This video is part 2, or an example problem for relative vector addition using subscripts that is like a chain of dominoes. And here's our problem. Here's a picture of it, kind of a sketch of it, and here's the word. So let's go through it. So first of all, we have a river which is 100 meters across, and it has a current flowing directly down it, and its current's flowing at 3 meters per second due east. Then we have a boat which is crossing this river, and the boat's operating at its top speed, which in still water is 5 meters per second, and the boat's rudder is set at 40 degrees west of due north. So that's the direction the boat's rudder is set at, 40 degrees west of due north. Now a person is on the boat, and the person is walking directly from side to side, so he's perpendicular to the direction, to the orientation of the boat. He's perpendicular to it. He's going from side to side, going from the right side to the left side. And so as he's walking across his boat, he's simultaneously walking up a ramp. So this is the top view of the person on the boat. If I was looking from the back side, and this is the view of the back side, here's the surface of the boat. This ramp he's walking from the right to the left side, he's also at the same time walking up this ramp, which is inclined 30 degrees relative to the horizontal. And the person can walk up that ramp at a speed of 2 meters per second. So, so 3 questions. What is the velocity and speed of the person relative to the shore? Question number 2, what is the velocity and speed of the shore relative to the person? And question number 3, at this condition, how long does it take for the boat to cross the river? So I'm going to pause the video now, solve it, and then we'll compare solutions. Now reviewing solution of the problem. The first thing is to determine what the required outputs are. And so we're asked for the velocity, the speed of the person relative to the shore. So that's the object person with respect to the frame of reference shore. And then the opposite that's asked, which is the velocity of the shore with respect to the frame of reference person. And then the third one is how long does it take for the boat to cross the river? So to cross the river is going from shore to shore. So therefore it's the velocity of the boat with respect to shore, and the distance will tell you the time. So now that we know what we want to get, the next step is to define a useful consistent coordinate system. So this is parts moving along in lines, so it's not probably going to be polar, it's more likely Cartesian. And then so I'll have my Cartesian coordinate system. There could be any orientation. It's going to be locked in space somewhere. Well, it needs to be locked relative to a inertial frame of reference, and the inertial frame of reference we'll use, which close enough, is going to be the surface of the Earth. So we'll make that assumption that the surface of the Earth is where we're going to lock this to. And most of the motion is going along on the plane of the water, which is the plane of this board. So it kind of makes sense that I'll have 2 of the dimensions, for example, the x-axis and the y-axis, be on the plane of the water. And so then using the right-hand rule, x, y, start with x, go to y, z is out of the board. So I'm going to have my coordinate system like this. Now the question is, probably it's easiest to line with something that you need to have. So that leaves us really 2 choices. Either I align it with the boat, and I have the boat kind of coordinate system, or I can align it with kind of like the velocity of the water, which is also perpendicular to the shore. And I think this is probably a simpler coordinate system to choose. So and that's what I've chosen. I said I'm going to say x is to the east or to the right, and so that's I hat direction. I'll have going this direction I'm going, the boat's going. I'll have that be the y direction, so that'll be j hat, and then the k hat or the z will be coming out of the board. And so this is my useful coordinate system. And now every object in that coordinate, so I'm going to have this is going to be locked on the surface of the Earth, so it can't move, and every object has to use that same coordinate system. So I can't have a coordinate system for the boat and have that for the river and everything else. So for every object, this is the coordinate system which is glued down to the surface of the Earth, and everything is measured relative to that glued down coordinate system. Okay, so, which has to be inertial. So I've now locked that coordinate system, so I know what my x, y, and z directions are. So now I've done the step 2, and the third part is kind of, now I know what I want in my coordinate system. I was told lots of information. So, for example, I was told, and we know this is a relative velocity kind of question. So I was given lots of relative velocities. The first one, I was told that the water is flowing to the east, which would be my plus I hat direction at 3 meters per second relative to the shore. So let's write down, I know velocity of the river with respect to the frame of reference shore is 3 meters per second, and it's in the positive I hat direction. Okay, the next thing I have now is, I was told that the boat in calm water, has a top speed of 5 meters per second, and the boat's going this direction. So velocity of the object boat with respect to the river, to the water, so the river, object boat to respect to the river, I know it has a magnitude of 5 meters per second. And I was told that the boat was going 40 degrees west of due north. So there's a 40 degree to it. And so now, if I have velocity of the boat with respect to the river, that's my velocity of the boat, and I want to figure out there's no component in the z direction, so there's no k hat, but there is. It's going this way in the I hat direction, so I know it's negative, and so if I think about the component just in the I hat direction, so that's opposite this angle, so I know that's a sine term. So it's going to be the magnitude 5 times the sine of 40 degrees. So that's my I hat, and it's minus, because it's in the minus. So minus 5 sine of 40 degrees is my I hat, velocity of the boat with respect to the river. And then I have a component, this is the y direction, so this is adjacent to that hypotenuse, the angle, so I know that's going to be a cosine, so it's going to be positive, so 5 cosine of 40 degrees in the j hat direction, meter per second. The last thing I have information about, I was told that the person, so the object person with respect to the boat, the person's walking from the right side to the left side, perpendicular to the boat. So the motion's 40 degrees this way. So I'm gonna have this 40 degree direction relative to the x-axis, and he's not only walking in that direction, but he's walking up an incline ramp. Okay, so this is the directionality of that vector. It's coming out of the board in this direction. So then I want to find the vectorial component that's in the I direction. We can see that's going to be a minus. And I was told this magnitude, this was 2 meters per second. So we know we're going to have a minus 2. And then we got to get the vectorial components both this direction and then the I direction, so that's adjacent to this 40, so that's going to be a cosine 40 degrees, so minus 2 cosine of 40 degrees. And then in the plane of the board, you can kind of see from this axis, I'm at 30 degrees elevation relative to the plane of the board. So in the x axis going this way, again I'm adjacent to this 30 degrees, so that's going to be another cosine. So I'm going to be minus 2 cosine of 40 degrees times cosine of 30 degrees in the I direction. And then in the y, I know it's going to be a negative again, so it's going to be minus 2, and this time I'm opposite the 40. This is my hypotenuse, and the 40 degrees is an included angle, so therefore it's going to be a sine, minus 2 times the sine of 40 degrees, and then the j hat direction is in the plane of the board. So again, it's going to be adjacent, so it'll be cosine of 30 degrees meters per second. And now the person is coming out of the board, which is in the positive j hat direction, and so that's going to be here. So that's just going to be this component over here. So it's going to be the 2 times the sine, because it's opposite, 2 times, it's going to be positive 2 sine of 30 degrees in the j hat direction, meters per second. So now that's all my information, all vectorially defined relative to my defined coordinate system, which is locked to the surface of the Earth. So now look at what we're trying to solve for. We want this velocity of the person with respect to the frame of reference shore. So I have some information here. I know, so I put what I want to have on one side, the equal sign, put the equal sign. I have to match the same objects here. So I need person, velocity of person with respect to something. Well, I have velocity of person with respect to boat. So I put the boat here. The frame of references don't match, so I'm not done. I always need to add when I'm doing this chain of dominoes or chain of subscript nomenclature. So I need to have a boat here for frame of reference boat. I need an object boat. Well, I have boat with respect to river, so I can put that river here. The frame of references don't match. Ship and river don't, shore and river don't match yet. So I need to keep going. So I know I need to match here. Frame of reference river, object river. And then I'm told, well, I have information about river with respect to frame of reference shore. So I put shore here. I end up with the same frame of references at the end and the same beginning objects. So this is now my equation, which I can use to solve for. So I'm going to take, so that's essentially these, so I'm adding all 3 of these. So I'm just going to take add up all the I components. So I'll take those values and stick it here. This value, stick it there. That value, stick it there. Then same thing for the j hat components, and the same thing, add up all the k hat components. So then you can just take your calculator and put that in there, and when you solve for that, you end up with minus 1.54 meter per second in the I hat direction. Take your calculator, do all that math, you end up 2.72 meters per second in the j hat direction. Take 2 times the sine of 30 degrees in the k hat direction, that's 1. So that's saying this is the velocity of the person with respect to the shore. You see it's good that velocity is in the minus I hat direction, in the plus j hat direction, and the plus k hat direction. So this is the velocity of the person with respect to the shore. Then the question is, what's the speed? So the speed is just the velocity is a vector, speed is a scalar, and so if you have any 3-dimensional velocity to solve for the magnitude, you take the square of each of the components. So you square the I hat component magnitude, square the j hat magnitude, square the k hat magnitude, take the square root of that value, and then you can that's the scalar, or the speed in this time. So I'd take these numbers, what I get, square it, take this, square it, take that value, square it, take the square root, so it ends up the speed is 3.28 meters per second. Second question is, what's the velocity of this object shore with respect to frame of reference person? Well, that's just the opposite of, as far as switching the objects in the frame of references. So if I do that, that equals minus what I've already have, the velocity of the object person with respect to frame of reference shore. So therefore, that velocity term, since it's just take a minus, I take a minus of whatever of each of the individual components. So the minus 1.54 becomes a plus, and this plus becomes a minus, and the plus becomes a minus again in meters per second. So this is the velocity of the object person with respect to the object shore with respect to the frame of reference person. Speed, these are these vectors have the opposite direction, but they have the same scalar magnitude. So the speed, again, would be the exact same value as we previously solved. The third question, how long does it take for the boat to cross the river? So the boat's going from one shore to the other, so I need to know the velocity of the boat with respect to the shore. And to cross the river, really think about it before we start doing any other work, is to cross the shore, any x direction or k direction velocity doesn't affect the time it takes to change across the shore. It's only the velocity in the y direction. So, but we're going to try, we need the velocity of the boat with respect to the shore. So that's what we want. So we write that by its side, on one side the equal sign. And then I'm not given directly velocity boat with respect to shore here. So I need to do my subscript object and frame of reference addition, just like the chain of dominoes. So I need to have the same object at the beginning. So I'm going to write down boat. Okay, then I look to see what information I have about boat with respect to something. Well, I have boat with respect to river, so I'm going to put that here. I don't have the same frame of reference here yet, so I know to keep going. I'm going to always add. I need to match this frame of reference to this object, so I know I have a river here. What information do I have about velocity of river with respect to something? Well, I have velocity of river with respect to shore. So I can add that up there. You see I have the same final frame of references, so therefore this is the equation I need to use. So I need to take the velocity of the boat with respect to the river plus the velocity of the river with respect to the shore. So I'm going to add up just these two components. This one gives me the I component, which I don't necessarily need to do for this one, because I'm not worried about how fast the boat's going in the direction of the current. I'm trying to what it's going from shore to shore. So you really need just this. But just as a reference, I added up these two terms for the I hat direction, and that turns out to be minus 0.214 meters per second in the I hat direction. This is my singular term for these two velocities in the j hat direction, which is plus 3.83 meters per second in the j hat direction. That's going that direction. This is the only one I actually needed to solve the problem. But this is the complete velocity of the boat with respect to shore. So you can see the boat with respect to shore is actually going in the minus I hat direction and the plus j hat direction. This one has no impact on its time to travel across shore to shore though. So I only need this velocity term. So and we know velocity is distance over time, and so distance in the y direction, velocity in the y direction. I can do the algebra here, multiply both sides by time, divide by velocity. So therefore time to travel across from shoreline to shoreline, the distance in the y direction is 100 meters per second. The velocity of the boat with respect to the shore in the y direction is 3.83 meters per second. I do that math and I end up with 26.1 seconds to cross. So hopefully you got these answers. If you didn't, remember to set your coordinate system up, lock your coordinate system to inertial frame of reference, determine what you want, use relative velocities, use the subscript addition rule, and you should be able to solve a problem and to treat things vectorially.